We're on lesson 5 of chapter 11, which is independent and dependent events. So first we're going to find independent and dependent events. Then we're going to find conditional probability. Then we're going to solve a multi-step problem. So here's the difference between independent and dependent events. Independent events are two or more events where one event does not affect the other. An example of that would be rolling a die and spinning a spinner. The outcome of my die has nothing to do with the outcome of the spinner. Dependent events is two or more events where the occurrence of one event does affect the other. So think of it this way. If you're choosing teams for recess and you have two captains, if the first captain chooses this person, well, the second captain can't choose that person. They can only choose one of the remaining four. So that first event of choosing her increases the probability that one of these other people will be picked to the next one. Let's do a little practice with that. It says tell whether each of the events is independent or dependent. First is grabbing a red marble, not replacing it, then grabbing a yellow marble. So in that case, does grabbing a red marble from the jar impact the probability that the yellow marble will be picked next? Well, yes, it would actually, because there's one less red marble in the jar now. So the likelihood of picking a yellow marble, although it didn't go up a whole lot, does increase. How about this one? Grabbing a green marble, replacing it, then grabbing a red marble. Would grabbing that green marble and replacing it affect the probability of grabbing the red marble? Actually, it would not, because you replaced it, meaning that there's the same amount of marbles now as there was in the beginning. And the probability for the red marble then remains the same. So that would be independent. This would be dependent. This would be independent. So in these problems, we have to determine whether they are independent or dependent and then solve accordingly. It says, as part of a board game, you need to spin the spinner at the right, which is divided into 8 parts. Find the probability that you will get a 25 on your first spin, and then 50 on your second spin. So these are two separate events. We have to ask ourselves, does getting a 25 on your first spin affect getting something else on your second spin? We would say no, actually. So that makes it an independent. They do not affect each other. So what we do is we take one probability at a time and multiply those answers together. Getting a 25 would be 2 outcomes in your favor out of 8 total outcomes. Getting a 50 on your second spin would be 1 positive outcome out of 8 total. We could simplify this a little bit. So 1 times 1 is 1, 4 times 8 is 32. So we'd have a 1 out of 32 chance of spinning a 25 on the first one, followed by a spinning with 50 on the second one. Now it says a bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and randomly choose another grape. Find the probability that you will eat 2 green grapes. So it looks like we choose a grape and eat it, and then we randomly choose another grape. Is this second grape impacted by the first grape? Actually it is, because there's one less grape now. So we need to pick a green grape first. So there's a total of 36 green grapes and 14 purple grapes. So that means that there's 36 favorable outcomes if I want to get a green grape out of a total of 50 grapes. And we're going to multiply that times the second one. So since I ate a green grape, that means that we're down to 35 after I eat that first one. Yet we still have 14 purple grapes. So my probability actually goes down a little bit of getting a green grape the second time. Not that much, but a little bit. That gives me 35 positive outcomes out of a total of 49 grapes now. Let's do a little simplification before we go. This is 18 over 25. If we divide both these by 7, that would be 5 over 7. Then we actually can simplify the 5 and the 25. This becomes 1, this becomes 5. So 18 times 1 is 18. 5 times 37 is 35. So here's the probability that you would get 2 green grapes in a row, a little bit over half. Now we need to find conditional probability. So conditional probability is the probability that event B, so the second event, occurs given that event A has occurred. It is written as the probability of B after A. For conditional probability, events A and B are independent because it's a given that A has already happened. Let's put that into practice. It says the weather table shows the number of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane, and B, the probability that a hurricane is in the northern hemisphere. So let's find the first and second event for this first problem. A future tropical cyclone in the northern hemisphere is a hurricane. So this would be the given. It's in the northern hemisphere already. So what's the probability that a cyclone in the northern hemisphere, event A, is B, a hurricane? So event A has already happened. We don't need to calculate that at all. But we do need to calculate the chances of a hurricane happening with all these storms. Well, our favorable outcome is hurricane, so that's 545. And that goes over 199 plus 398 plus 545, 1142. Then if we do our division, that gives us a probability of 0.477, we'll say. So 0.477 or 47.7% if you want. So that's problem A. Now let's solve problem B in blue. The probability that a hurricane is in the northern hemisphere. So event A is that it's a hurricane. So that's already a given. So now that it's a hurricane, what is the probability that that would be in the northern hemisphere? So here's the hurricane data. The favorable event would be the northern hemisphere, making it 545. And that would be out of 545 plus 215, which would be 760. So the 545 out of 760 would be our odds. So let's do our division. So that gives us a 0.717 probability. So given that it is a hurricane, the probability that it would be in the northern hemisphere would be 0.717. Now let's solve a multi-step problem. It says, using observations made of drivers arriving at a certain high school, a study reports that 69% of adults wear seatbelts while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt, and 26% of the time when the adult does not wear a seatbelt. What is the probability that a high school wears a seatbelt? So these do sound like dependent problems because it's all dependent on the adult driver, as we can see. So I guess this would just represent the probability. We have adults that either wear seatbelts, which would be 69% wear it, and that makes 31% who do not. The high schoolers with the adults that wear seatbelts, 66% of them wear seatbelts, and that makes it 34% who do not. With these 31% of adults who do not wear a seatbelt, 26% of the students wear a seatbelt, and that must make it 74% do not. So we're looking for the probability that a high school student wears a seatbelt. That would be our favorable outcome. Well, what is it? Well, we have this combination here, I guess, 66% of the 69%, and then the 26% of the 31%. So if we added up these percentages together, that would give us our total amount. So 0.69 times 0.66 is 0.4554. So this gives us 0.4554. 0.31 times 0.26 is 0.0806. So if we added these together, that would give us a snapshot of how many high school students wear seatbelts. So we have the 0.4554 plus the 0.0806. That gives us a decimal of 0.536. If you want to make that a decimal, that would be 53.6%. And that would be the percentage of high schoolers that wear a seatbelt.